Welcome to 2024 spring term, and this is a class called Emerging Technologies for Lifelong Learning. Just rough idea, which year are you guys in? First year, mostly first year. Okay, very good. Okay, I would like to start by asking you a simple thing. You are here by definition to learn. Okay, you're here by definition to learn. That's a given. And then there have two questions: what to learn and how to learn. Okay. Now, how to learn, you may have heard a little bit about the BASI program, where you learn by doing, you learn by project, by interaction, by prototyping. There's a lot of that, right? So you may have already been orientated a little bit about how differently we do things here. Okay. But I'd like to get back to a very simple question of what to learn. And here's where it becomes relevant to our class. Okay. So my question is, what to learn? Well, there are actually two things you learn. You either learn what or you learn how. Okay? You learn what or you learn how. Now, I maintain that this is my breakdown. I'll just give you the answer. Okay? 80 to 90% of what you learn is how. Okay? Only 10 to 20% of what you learn is what. I'll elaborate on that later. Okay? Likewise, when you go to learning how, okay, 80 to 9% of how is exactly that. It is how. And 10 to 20% of how is what. Okay? Let me get rid of some simple thing. Okay? Let's say how. How is, how do you get a job? Or how do you go to the interview and impress your potential employer? Okay, there's a lot of things about that is literally about how to answer question and how to interact with the questionnaire and so forth. But there's a tiny bit of how that is what. In other words, what you wear tells you already. So how is already what. Okay, there's a little bit of that. There's a little bit of that. Okay, so if the how is how to interview, and what you wear is, I don't know, a pair of jeans and very loose tighting shirt, it either signals that you are idiot savant, or you really have no manners and you don't really care for the company. Likewise, they're not going to care about you. Okay, so it's a little bit of that. Okay, so punctuality, how you dress, what you wear, your hair, whatever, that's already in the what. But that what answers how. Okay? And most of learning how is literally how. In other words, you learn how to do calculus, you learn how to do data analytics, you learn how to do pitching, you learn how to do lab, you learn how to do biological experiment, you learn how to prototype visualization and so forth. So a lot of how is really just how. Now let's go back to what. Okay? Let's go to what. Now, most of what you learn is also about how. What do I mean by that? When I teach you in this class, let's say I'm going to teach you about quantum computing, which is one area of emerging technology. Okay? If you come away with being able to cite like a Wikipedia kind of thing, quantum computing is based on qubit and all that kind of stuff, okay? Then you haven't learned anything, okay? Because the what of quantum computing is how quantum computing works. The difference in the how on top and the how on the bottom, the how on the bottom is how you do things. In other words, you actually learn how to do things. When I teach you, learn what, and that what is quantum computing, in BASI at least, you're not doing quantum computing yourself. Okay? But the majority of what you learn would be how does quantum computing work? Because if you know just about the facts about quantum computing, how many companies there are, it's based on qubit and superposition and entanglement and all that stuff you can read from Wikipedia, you haven't learned it, right? You haven't learned it. So if what you know is replaceable by an answer from ChatGPT, or what you know is replaceable by a page from Wikipedia, then you haven't learned, okay? Because you haven't learned how, okay? And of course, 10 to 20% of what is literally what. That would be like, when you learn geography, the capital of France is Paris or something like that. That literally what you learn is what. And that's what sometimes educator gets confused. They say, learning is not about memorization. Well, that's because it's that 10%, that 10 to 20%, where you literally learn to memorize simple fact, no relationship. Not how things work, not relationship between objects, but what's the capital of Paris? Okay? That sort of thing, that factual thing is immense. You can't learn it all, and you don't need that. And that's the bit where you say, learning is not about memorization. It's not about memorizing those tiny facts that you can look up. But you should know this based on neuroscience and modern research about psychology and neuroscience of cognition. Everything about learning is memory. The whole job of you coming to Basai for 4 years to learn stuff is to form memory. Because memory is the only way something external property to you becomes internal to you. How to play tennis is a general property of the world. Once you learn, you have the muscle memory. That's how you learn how to play tennis. The tennis playing becomes inside you. So the only way you can internalize anything of value in life is memory. Okay? But just understand that it's not the tiny, not the meaning in the simplistic sense of, what's the capital of Paris? That's rather silly. So let's get that straight. So that's the mode of learning that some of you, are not familiar, are not made aware of. And there's reason why, people mock things like, memorization is not important. No, memorization is everything. It's the mechanism for memorization and the thing about the system that you memorize. If you memorize fact, too bad. But if you memorize relationship, functional relationship, functional link between X and Y, okay, then you're good. Okay, so let's so we have to and the reason actually this is something that could serve as a preamble to the Basai program as a whole. But the reason it's important for this class here is this. Okay, this class has to struggle with this. Okay, in other words, what you learn, okay. Oops, I may have misprinted actually, sorry. So that's what's what. Yeah. My typo. So it sounds a little bit silly. Okay, so that's what I was talking about. Okay, fine. Here's the thing. This class, what's the name of this class? Emerging Technologies for Lifelong Learning. Now, we can be actually democratic about this. You guys can take a vote. Okay, you can take a vote if you like. I'm game. You can say you're here to learn about emerging technologies. And then we focus on this bit. What is how? How does quantum computing work? How does cryptography work? How does machine learning, generative AI works? This is the emerging technology that we're talking about as a subject. It's emerging technology for lifelong learning because the technology hasn't stopped and it will not stop in your lifetime. That's the meaning. Okay, that's the meaning. So you're here to learn about what? About emerging technologies. And when you learn what, you actually learn how those technologies work without operating the quantum computing machine yourself. Okay, maybe you have some sort of like a play toy problem with it, but you're not going to be in a IBM research lab. So that's one way of gaming this class. Here's another game. You can start with lifelong learning. Okay, so you are here to learn how to be a lifelong learner. But you apply lifelong learning not to basket weaving or opera singing. You're learning lifelonging on how to learn about technologies that changes all the time, i.e. quantum computing, machine learning. So that would be you're learning how to be a learner, how to be a lifelong learner. Okay. Now, the way I designed this class, I've always designed this class, even 2 years ago, is how to be a lifelong learner. Okay, how to be a lifelong learner on emerging technologies of your choice. Okay, so the focus again is on the modality by which you acquire knowledge, by which you form internal memory about how emerging technologies work and where it's going or whatever. Okay, so just so you know, this is what I'm aiming for. Okay, this is what I'm aiming for. Now, you can say, I have something particular about emerging technology area, I want to go in depth. Then you can use that as an exercise. Okay. So this class, unlike most other class in Basai, you're learning how, literally how in yourself. Okay. When I teach you data analytics, it's a bit of both. Some of you are doing the analytics yourself. Some of you are understanding analytics, how it works, how analytics work. So the important thing here is, if I circle the word how on top here and the word how on top bottom here, you know that those are two different hows. Okay? How things work or how people work at things and how you work, how you do it yourself. The confusing bit is that a lot of time learning how things work, the exercise you would do it yourself, but you do a very tiny baby problem version of it, right? So it would be like, I'm just being funny here, but let's say you're learning aeronautics, and I ask you to fold paper plate just to see that, angle of attack and so forth, something like that, okay? So you're doing how yourself. You're learning the how yourself. But what you're learning is not good enough for you to qualify as a proper aeronautics engineer, okay? You're just getting a glimpse. So the basis of Basai, okay, unlike most, let's say you're in the engineering class, when you learn how, you literally how is how, okay? How do people mill machine? How do people build gyroscope? How does gyroscope work? How do you build it? You build it as an engineer, okay? Here, how gyroscope work, you will not build gyroscope. You'll not be in the gyroscope engineering business, but you will be in the business of using gyroscopic information for something else. For example, you know that there is a little gyroscope inside here that detects a motion, right? And then you use it to do motion sensor, okay? So most of what Basai does, again, I repeat, most of what Basai does is what, but what is how. In this class, the way I design this is literally how. How is how. How do you become a lifelong learner? Okay, are we clear on this? Okay, so spiritually, I want you to orient the thinking a little bit. Okay, that's the thinking. Now, again, before I go, just let me lay out the game rule, decorum. I do expect you guys to be on time. Being on time is one of the easiest things modern human beings can do, because everybody has got a watch. Well, you don't even have analog watch, you have digital watch. Okay, your watch is actually synchronized to the machine that is based on a cesium vibration. That's put like gear down to a second. So, you know, there's no reason for you to be late. Okay. I would treat you as adults, but young adults. Okay. So we have to have mutual respect. By the way, that's very important. I try to do this talk to orientation class. It's very important, no matter how brilliant you think you are, to actually be courteous and respectful, okay? And that's why you guys have to wear a uniform. Rule of thumb is, if I'm giving you knowledge and I'm not comfortable because I'm wearing a shirt, you should be even less comfortable, okay? So even in the old days, it would be like, I wear a shirt, you wear a shirt plus a tie to make it more a little bit more uncomfortable. So if you're getting knowledge from me, you should be less comfortable than me. If you're applying for a job, and the job interview at 9 o'clock, he comes in at 9 o'clock, you should come in before, maybe come in at 8:30. That's actually called connectivity between human beings. Okay, so that's literally how. Okay, so do that. A lot of this symbolism, uniform and dressing right and being, you know, it looks like formality, it means nothing, but it's a signaling. You haven't been taught the signaling theory class in communication, but it's literally that. For example, I'll give you an example. This is a fun example I usually give. You know, like say in Thailand, like 8 o'clock or something, there's like a national anthem, right? And people stand for 2 minutes. Completely, you think it's completely pointless because why do you have to stand for 2 minutes, right? Because you can actually love the country and be willing to defend the country, like, you know, Russia invaded Ukraine, you know, you'll be the first to join the resistance or something like that. But here's a signaling part of it. If you can't sacrifice 2 minutes of Facebook time or TikTok time to stand still for something else beside yourself, do you think that when push comes to shove, I can rely on you to save the motherland? No way. That's why human signaling makes a lot of sense. Okay, so a lot of this little thing like institutionalism and dressing well, being on time, you think, well, you know, I'm so smart, I don't have to come to interview on time. I'll still answer the right answer because by the time I get there, I already know the answer. I'm really smart. That's not it. That's not it. Okay, so this human signaling is very important. It's not part of this class, but well, it is a little bit. So right now we are clear. Most of Basai, you learning what? But when you learn what, you actually learn the what is how things work, how quantum computing works, how technology works, how it impacts you, how you can make business model out of something that's already invented. But this class is how. So you're learning about how to be a lifelong learner. Okay, so let's go to that. So that's just a little introduction. Okay. Boop, 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 boop. Where are we? We need to go to the slides. Let's go to should be emerging technology for lifelong learning. Oh, okay. Let me go to the version that's kind of closed, so I can kind of like release a little bit of time. Now, and this is what I want you to be prepared, I guess. So that's you guys, and that's you guys, that's you guys. And let's go to this little mind map. Okay. By the way, I don't use PowerPoint. Okay, I use PowerPoint strictly for business presentation. And I may have told some of you already why I do that. PowerPoint is extremely useful for business presentation because it linearizes the narrative. Why do I want to do that? Because I want to open with, you have a problem, and end with, your solution is my company. Okay, so I don't want any kind of divergent thinking. I don't want any kind of forking left and right. I want a line, a straight line from you have a problem, it's so important, I have the solution, pay me lots of money. Okay, that's why I use PowerPoint. Like I'm not here to sell you things. Okay, I'm here to actually expand your mind. So I will, it's occasional when there's some subject that I already prepare a PowerPoint for something else, I might use it because I'm lazy. Okay, right. So let's go to where we are. Okay, let's go to where we are. Now, just to give you a head start, in this class, the way you prove that you have learned, how to be lifelong learning, is to pretend right now you're out of college, you graduated from Basai, and you want to be in the nanotechnology or nanofabrication game. Okay, as an outsider, how do you go in without being completely superficial? Okay, that's what I would like you to prove. So each of you will, we might do this as a group project, but I would prefer individual project. Pick up some kind of area. Okay, so the emerging technology area would be something like protein folding for you, or transcriptomics, or whatever. Okay, and then how do I get in the game? Okay, how do I get in the game? Now, of course, a lot of these games, scientists, technologists, engineers have worked on it for years. So who are you to just read Wikipedia page and ChatGPT and understand it? How are you going to do that? That's not the point. The point is that if you have a basic literacy, okay, what do I mean by literacy? You understand English, documents are written mostly in English, okay? In the future, maybe Chinese, I don't know, but right now, you have English literacy, you can read technical document in English, okay? You have mathematical literacy, you know when variables interplay in whatever model it is, you can understand what it means. Calculus gives you the rate of change or accumulated through integration, okay? Randomness expresses itself through probability model, probability distribution, okay? Things like that. So these are the mechanical literacy you have to have. English, right? Mathematics, probability, statistics, model. I think this thing is not. Is it okay? Yeah, okay. Programming or algorithmic literacy. Okay. Programming and algorithm are different, right? You use programming to write algorithm, okay, but you may use different language, different programming paradigm. But the gist of it is you understand the algorithm behind it. Excuse me. Okay, and then you have some basic understanding of the mechanism of biology, from genetic RNA, DNA transcription, all the way to protein synthesis, all the way to the bodily function. You don't know as much as a biologist does, but you certainly know the principle. Okay, so you have to have all this foundation, literacy about how life works, how evolution works, how business works, how government works, okay? And then the particularities, you would sort of like dig in. And that's what I mean by lifelong learning, right? Now, what's the limitation? Where would you stop? You would stop at development. In other words, I expect you to be able to go to any reasonable area, okay? Maybe advanced particle physics is beyond you, but anything, okay? Quantum computing or something, you would get to the level where you understand how things work, and you can see the trajectory of how this technology is going to pan out. Is it going to be worked out in a couple of years? Is it relying on something that's not likely going to be solved within your lifetime? That sort of thing, okay? You will stop at development. In other words, you will not be in the driving seat developing nanotechnology. You will not be in the driving seat developing protein folding algorithm, okay? That's it, you stop there. Okay, so you just basically remember that picture I showed you about learning what is how. Okay, so you're learning how so that whatever you comes in, you can learn how it works by yourself on your own. Okay, and use this class as a practicum kind of thing. Try something. And I'll give you an example. When I was, I guess, a student in high school, right? You have to write essay. Okay. Now everybody just picked up any random essay topics that they want to learn, that they want to write about. That's easy to write. But I took it differently. I took it as opportunity because I had to write a research paper. I might as well research something I wanted to do. So at that time, I think I was interested in abstract art. So I used abstract art as my object to exercise my English homework. My English homework was to write research paper about anything. So I might as well choose something that I wanted. I've always wanted to know what abstract art is all about, right? You should have that kind of thinking. Okay? Anything that you think is interesting, a little bit beyond you, a lot of you would probably think towards something like ChatGPT or something like that. That's fine. That's fine as well. Okay? I mean, chances are, there are what, 20 of you. So few of you will have very, on a broad level, same kind of thing. So it'd be like generative AI. But then you go to different aspects of generative AI. There's plenty of stuff to go around, don't worry. Okay? Okay, right. Okay, so let's go to the, I guess, the meat of the matter. And since it's going to be about emerging technology, your final product will be something like white paper or research paper or survey paper on the very thing that you are trying to learn about. Okay, it's an evidence of your quote unquote guided learning. Okay, the only difference here is that once you be on Basai, I wouldn't be here to guide you. You guide yourself. Okay, so this is an experiment of self-learning with supervision.
So it's like individual assignment, or
I would like it to be an individual assignment, but for practical purpose, might have to do groups. Let me think about it. I'll discuss a little bit about that. Okay. Yeah, personal assignment is best. Because this is not about trying to produce something that requires different talent set. That will be teamwork. This is about you trying to penetrate into a subject. Okay, so you want to get in there. Okay, it's not about a whole bunch of you getting in there, but for practical purpose, might have to do groups. We'll see. Okay. Excuse me. I'm had a cold. Had a COVID, then a cold, and so I'm not really recovered. Okay, so let's talk about definition. Okay, let's talk about definition. Okay, there are two words. Might as well say emerging and technology. Okay. I will have program for you to play with, and sometime in class I will have you sort of like play along. But until then, I don't want you to be, looking at your own computer, whatever. I want you to focus on what I'm saying up front. Okay. Okay. So I don't want you guys over there. Okay. To work on anything on your computer, just close it. Good. Right. So what do we mean by technology? By the way, could there be a program called Bachelor of Arts and Science in Integrated Innovation that has nothing to do with the new technology? Certainly. It's very much related to innovation, but technology and innovation are two different things. They often intersect. Okay, so let's go look at what we mean by technology. Okay. Let's look at a few concepts. First of all, by definition, there's only three things here I want to look at. Technology has to be, well, a product of human beings. Okay. Sometimes we talk word like nature's technology when nature produced lava and has any. That's not technology. Okay, we use it as a sort of like a nice word to say. But in technology is a human artifice. Artifice means something we create. Art, artificial, artifice, architecture, all these have the same root. Okay. By the way, I really like etymology online. So look up the word artifice or architecture, and you see the word art pops up. It has to be anthropologic. In other words, it's basically it came with man. Okay. No technology came before man. Okay. Everything else becomes something we discover as a process, as a mechanism. We can adopt that. Okay. So synthesis, if we invented how to synthesize calories from sunlight, that's our technology. But photosynthesis is not technology. Okay, that's just how nature works. Okay, nature is smart enough. Second, it's also a manifestation of scientific principle. That's very important. In other words, when you want to ask, is this a piece of technology or just a know-how? Okay, a piece of technology can trace ultimately back to some scientific principle. Okay, so bicycle, you can always trace it back somehow to leverage, right? Gearing, all kinds of stuff. So it doesn't matter. Anything that you can label a technology, A, came from man. B, it is not necessarily the direct, it could be indirect, but it has to be able to trace back to some scientific principle. Again, discovered by man. Okay. And the third thing is, it has to be driven. In other words, because we don't create it because we're just hungry. Okay, when we're hungry, we go get food. When we're hungry, we don't create technology. So technology has to be driven somehow. There has to be some kind of organizing principle why human beings invent technology. And basically, there are two ways, open-ended and closed-ended. Open-ended means what you often hear, necessity is the mother of invention. You need something. Piece of technology is needed because human being wants to travel across ocean. How do we drive boat across ocean when we just got wind and your hands? Something like that, right? So there's a means to an end. That's what happened. But conversely, a lot of time, things just opens up. Possibilities opens up. And you see that a lot. Okay, you see that a lot. In fact, most of the game changing, and I don't know if you realize this, most of the game changing innovation, things that really affect your life, were not invented to do anything. It's just a series of discovery, and you got this and you got that, and then, hey, why not this and that? It's an open-ended synthesis. Okay, so it's driven, but it's not driven necessarily to a goal. That would be the first point. Driven to the end. So a good way of checking your understanding, let's say, for example, whatever it would be, give me an example of technology that was invented toward an end, as a means to an end. Give me an example of technology that just arrived because of confluence of factor and people start doing things. Okay. So for example, if you say internet was invented as a way for people to trade, like e-commerce, that's a silly question. That's a silly answer. Because internet was not invented toward an end. Internet wasn't invented, let's have some e-commerce. That's not what happened. Okay, same with semiconductor, same with computing, everything, a lot of things. I would say this, the more ancient the technology, the more likely it's gonna be of this form. Like you need to travel, you need to store grain, you need to fight off animals. Okay, it's a very direct one-to-one between what you need to do and what you need to invent to do that. So in the ancient technology, there's a lot of means to an end. The more modern piece of technology, silicon, digital computing, nanotechnology, the more likely it's going to be something that's invented for its pure sake, from scientific curiosity. And then people put bits together and become something applicable. Okay, so this is a story of the modern time. This is a story of the more ancient time. It's not hard and fast, but roughly. Okay. Before we get to individual topics, so let's get a little bit to historicity of it. Okay. Well, first of all, let's look at when I talk about humanity, right? Came before human. So let's talk about epoch of humanity. Let's say humanity, roughly speaking, okay? Roughly speaking, divided into 5 ages: stone, iron, bronze. Industrial, you can say that's kind of steam age, steam engine age, and silicon age. Okay. What's the thing about stone? The thing about stone is permanence. Okay. Before stone, nothing was permanent. Everything you eat in the morning becomes poo-poo in the evening, right? Down to the animals, down to the everything. Okay. But then you invent tool, you have stone tool that you don't use once. It's not a disposable axe. You use a stone tool, you use a stone you use today, you use tomorrow. Okay. You build some kind of architecture, you can live it, use today, use tomorrow. There's some kind of permanent, there's some kind of thing that you can create and it works. Okay. So that's you can say that's what Stone Age achieved. Now, what about Bronze Age? Well, with Stone Age, anything you make, you have to chisel out of stone. So whatever shape you have has to be inside that, right? Okay. You can never make a sword out of stone this big. Maybe you can make a sword out of stone this big, right? You can't make a sword out of stone this big. But certainly with bronze, you can, because you can melt it and stretch it, right? So human beings start to master shapes. Okay, shape becomes something that's so we're talking about ability to, we're moving to a technology. Okay, so before that you didn't have permanence, now you have permanence. Before Bronze Age, you didn't have a way of manipulating shape. Okay, in physical object like this, you can certainly like put leaves together or something. Okay, what about Iron Age? Well, the thing with Bronze Age is that it's not as strong. Iron Age is where you actually have something that is physically way beyond anything human beings ever imagined in terms of strength. Okay, you can say that bronze things probably as strong as animal bones or something like that. But once you get to Iron Age, it's not just iron, it's steel. We're talking about steel, different between iron and steel, right? So when you say Iron Age, I'm talking about steel as well. Now we get to Industrial Age. What do we get? We have scale. Everything about Industrial Age is about scale. Everything you can do, once you put an industry to it, you can do it 1,000 times better. So agriculture becomes agricultural industry. Right? Right? Fighting becomes defense industry. Okay? So once you industrialize it, it grows at scale. And this is where, your friends from economics department talk about, division of labor and Adam Smith and all that. Okay, so that's gonna sort of like what you extract from this. But basically, it's about scale. Okay, and scale is only workable because you have society. But, we're not talking about the anthropological aspect. We're talking about technologicals. Okay, so what can you achieve? You can achieve permanence. You can achieve shape or shape manipulation. You can start to achieve strength beyond anything that nature has ever seen. Okay, stronger than animal bones, stronger than tree, stronger than iron, just raw iron, but smelted iron, steel, and then scale. Okay, nature produces corn, but not at industrial corn. And then you get to silicon age. What is the thing that we haven't been able to manage before? What is the currency, so to speak? Okay, for reference, if you want to go to, you have to ask for permission. You just don't walk out, okay? Information. Information becomes a thing that we didn't have before. Okay, now you can say that in the Iron Age, Sumerian, they were already collecting data about the harvest. So there was some information, okay? But it didn't take on the life of its own, okay? Certainly, nobody was selling data, okay? So data wasn't a commodity. The commodity was grain, and you sort of collect it with saying how many bushel of wheat and whatever. But now information is a thing in itself. It's a thing that drives things. It's a thing that drives boom and bust of an economy. It's a thing that makes somebody rich, makes somebody poor, makes a factory viable, makes a factory close down. Information. Okay? So you can think of epoch of humanity. Now, where are we? Obviously, we are actually in the information age. So a lot of what you do will predicate on the ability to operate on information domain. Now, think about scale hasn't gone away, right? You still need to produce iPhone at scale. Nobody's making iPhone at home, right? So scale industrial is still here. It's not here, okay? But the emergence of the key currency of technology is information, okay? So Apple didn't become Apple because it can make this machine more efficiently. That's just manufacturing, right? So it's about ability to harness information. So even I'm talking about things like nanotechnology. Nanotechnology is very physical, right? Right? But still information. Because how exactly do you get resolution at easy level like this down to resolution at atomic scale without losing the fuzziness, right? Without becoming fuzzy. That's information retention. Okay? So it's easy for me to write number 1 and 2 with my pen. Can you write 1 and 2 with atomic, silicate line up into letters? Okay? So in a way, the thing that overrides it is about randomness versus information. So still it's information. Everything here, information. That comes down to information. Okay? Side note, even black hole is about information, but that's something else. Any of you guys are into physics? Huh? Okay. So historicity, look at that. Now, the frontier of knowledge. So we talk about this humanity, right? See, how should I get louder? So there's something about the microphone. So this here is about the Stone Age, we achieve permanence, Bronze Age, achieve shape, Iron Age, strength, Industrial Stage, scale, Silicon Age, information. Now, when I talk about frontier knowledge, I'm talking about, what is the game changer? What's happening? What's happening? Where do you apply all these things? Well, when you go back early, then it becomes things like husbandry, right? Husbandry, like farming, plants germinate. How do you do that? So instead of going and gathering plants from the forest, you can actually gather seed, put in the backyard, gather the fruits in a few months. Animals breed, so you can breed animal for strength, for beef, for protein, for milk, whatever, okay? So those are where things apply, okay? So all those tools that you apply, Bronze Age, you make a sword. What do you make a sword for? You make a sword to make a thing to, harness your cattle, okay? So it's sort of like area of application. So frontier of knowledge could be this. Now, later on, it's about material. And this is where you discover elements of nature. Iron stronger than steel is stronger than copper. Copper is conductive and all that kind of stuff. So it's about mining, production, industry. These are the two things that is still with us. One is mechanical leverage. One is energy can be harnessed. These are concepts that were not there before. If you think about it, let's say, go back to the Stone Age. Right? They built a ship, harness the power of the wind. Okay, that's power. Immediately, the wind applies to the sail, the ship moves. But energy is something that can be harnessed, can be stored. And when you burn it, yeah, you get power, you get torque, you get things like that, right? So the fact that there is something inherently quantitative about a lump of coal. Okay, it's not like wind. Wind immediately drives the sail, but coal is something that just sits there. But once you burn it, it can generate steam. Steam can generate propulsion, drives the ship. The idea that energy is a quantity that you can harness. This becomes a theme. Okay, this becomes a theme, and the other theme is called mechanical leverage. This is idea that little things can move big things and all that. Okay, so what is your theme? The theme here is something that you cannot see at its subatomic scale. So this will become your theme. So what I'm trying to do is lay out the what we call landscape of knowledge. Okay, now notice all this you can see with your eyes, right? Mining, property of silver, gold. Yeah, you can see that. Mechanical leverage, you can see a cow moving and stuff. Anything can be harnessed, you can burn coal and make a steam engine. But now you can see electricity. You really can't, right? It becomes something that definitely comes from scientific discovery. So all the things that's happening in your realm right now, no question, begins in physics. Okay? A lot of you may argue a lot of things begins in biology. But I would say, if you're gonna have one thing that's the mother of everything, it's physics. Yeah? So you have electricity. What's electricity? These are moving electrons that basically manifest power, energy, all kind of mechanical work, electrical. Electronics are different. Electronics is not electricity. Okay? Electronics is like using electron not to drive stuff. Okay? Electricity is like using electron to turn a fan. Okay? Electron drives stuff. It delivers energy. Electronic is not about delivering energy. It's about processing, right? It's about logic gate. It's about making decision. You have analog. Don't have to worry. I put this down for completeness. You don't know what analog electronics is because you were not born. Okay, but I can tell you that we used to be able to fire rockets from a ship to another ship, not very precisely, using vacuum tubes. You guys know what a vacuum tube is? That's analog electronics. Okay. Anyway, that's history now. Now it's digital. Digital comes into your life in two ways. One is basically digital controller, the other one is digital computer, and that's a whole bunch of things, okay? So now we get to the realm of electron doing stuff. How does it do stuff? It does stuff by logic gates. How does it do that? Because we make pathway for it. If electron goes this way, you flip things from 0 to 1. If it doesn't, then it stays 0, and then so forth, right? So you actually set out a game, a little game for electron. Electron doesn't do anything, it just flows, right? Let's say electron just flows. Oh no, I'm just flowing. Okay. So imagine if instead of having gerbils that runs and turn a wheel, you have gerbil that turns logic gate. Electrons are those gerbils. So you manipulate the platform so that when electron does what electrons do, which is move things, move from, toward a positive anode, it does logical computation for you. Okay. Now, what else is the game? I said molecular biology because I want to distinguish it from, macrobiology. Okay. Basically, there are two things it's actually the same thing, molecular biology, whether or not cellular or genetics. But the reason that I separate the cellular genetics tends to be because specialization. People who are cellular biologists, they go one building and geneticists go to another buildings. Okay? And inside the buildings where they house all the geneticists, they have geneticists, transcriptomics, research, proteomics, and all kinds of stuff. So it's a whole bunch of stuff. Once again, these are not things that you see at the macro level. So it's a very micro molecular level things that are operating. Okay? So anything is going to happen, it's going to happen on that scale. Okay? Well, you have electrons, right? And then you go to the thing inside, right? You have this basic idea of electron whizzing around the nucleus, right? Well, you go to the nuclear process, you have nuclear process. Here I separate two problems, two domain. One is uncontrolled reaction, meaning things that happen on a nuclei level. Doesn't involve electrons way out there. Just go to the nuclear, okay? And nuclear here has proton and neutron, and the number of protons that stick together to make this lump versus separate together make two lumps, or two lumps coming together to make one lump. That's what we're talking about. So there's a fission, meaning big lump separate into smaller lump with leftover energy. And there's fusion, smaller lump fused into big lump with leftover energy also. Now, I call this uncontrolled reaction because it's a bomb, basically, right? And you guys know, by the way, most of you don't even know this. What's the difference between atomic bomb and hydrogen bomb? You almost get good answer if you say atomic bomb is fission, and this one is fusion. Except you can't make a fusion bomb without fission bomb. So what happened is inside atomic bomb, I don't know if you watched Oppenheimer, you need a little explosion to push things together, and that things together will fuse at nuclear level. That's fission. Oh, sorry. Fission, yeah, fission. That fission is strong enough to make a bomb. To make a bigger bomb, you use regular bomb. To make fission bomb, you use the fission bomb to drive the fusion bomb. So you can't say hydrogen bomb is purely fusion. Just like you can't say atomic bomb doesn't have TNT. It does have a little bit of TNT. It's not TNT, it's probably something more advanced. But basically, regular explosive in there. So you need small, ordinary explosive to make atom bomb. You need atom bomb to make hydrogen bomb. And that's why this one is still dirty. If you actually have atomic bomb, you have leftover radioactivity. If you have pure fusion bomb, you don't have leftover radioactive stuff. You don't have to worry about it. But because in order to ignite the fusion, you need the fission, and that fusion has radioactivity. Okay. So anyway, you die either way. Okay. Okay. Well, then you have controlled fission. Fusion. Why am I saying that? I keep doing this silly mistake. Also, you're right, fission. Because we don't have controlled fusion yet. Controlled fission is energy. Okay? And that's pure controlled fission. What it does is just you have a way of regulating it. Okay? Now, if you look at nuclear power plant, this is very macro stuff, very huge thing. But things don't happen at macro scale. That's my point. My point is it doesn't matter, even though the nuclear factory is as big as Chulalongkorn campus, let's say. Okay? It doesn't take place on a macro scale. all the fission and fusion happens at the molecular scale. In fact, this is below molecular, right? Molecular, atomic, and then you get the electron shell, and you get to the nuclear. Okay, so we get down to as deep as we can. That's it. We don't get deeper than that. This is as small as it gets. Now we get back again, bigger. Nanotechnology is not nuclear. It's actually atomic and molecular. Okay? But the difference is now you are trying to manipulate. So you can actually line up little atoms to spell hello or something like that. Okay? Whereas before that, it's quantitative, like I control the quantity of electrons, right? I control the state because electron flip the state from 0 to 1, okay? But what I do not do is place atom piece by piece. I don't have this kind of manipulation. So this thing is on a bigger scale than this thing, but it's also tougher maybe because you're not just controlling the quantity and flow, you're actually making positional adjustment, right? And that's why you have this nanotechnology. Now, quantum computing, oops, I can go there. Quantum computing, it's even worse because actually you go bigger, okay? The quantum substrate is not necessarily that small, okay? So you don't go to the nuclear level. You could, but anyway, you manipulate things like laser and solid state or something like that. Sometimes some kind of quantum substrate. Never mind, small stuff. Still, you cannot see, okay? But you are not just manipulating. You are actually, you're not just manipulating position. You are manipulating interaction. Except quantum interaction is a little bit weird. It has this thing about, entanglement and superposition and stuff. So you're still trying to manipulate it. Okay, but it's really queasy stuff. It's really hard stuff. So those are the realm that you're working with. So as a subject for this class, chances are you're not going to be doing a term project on, I don't know, coal power or something like that, right? Chances are it's going to be in here, but this as well. In other words, this thing about energy is still part of your game, and you go back to material as well. Except it's not going to be material level like stone versus bronze versus steel, right? It's going to be something more advanced, right? Material science. Okay. So carbon fiber, carbon matrix, and if you have nano carbon tube, that's also nanotechnology. But even if without nanotechnology, material science is a lot more advanced than bronze, stone. Good example would be all the alloys. Okay, all the alloys are very simple. It's just one metal with other metal with other metal. Okay, but they have different property. Okay, titanium has certain percentage of this and that, aluminum and cadmium, right? Yeah, and they have different property just simply by the molecular ratio alone. Okay, so all this, and then back to husbandry. Okay, things about plants grow fine, animal breeds fine. Let's not talk about animals. Let's talk about plant growth. Plant germinate, plant grows, but what do we need for plant to grow effectively, right? So you can use drone to monitor plant health. You can use little stick of hygrometer, stick into the ground, and have a remote sensor telling you if you need to add water. Okay, so precision farming goes, the word farming goes back 2,000 years, but precision farming is only 50 years old. Okay, it starts a little bit like, probably Israel is a good place to start because Israel was in the same land as basically desert. So what they do is, instead of just watering plant, they just drop little bits of water at the root. Okay, so no loss. You don't get it to evaporate. So you don't water the field. You actually deliver the droplet of water to the plant. Okay, start from something like that. Start from something like that. Okay, so precision. So all this area, unlike this, okay, this is, presumably you are here now, right? You're in this age. You don't go back to Iron Age, but here everything is gained. I'm just saying that the exciting, high-tech stuff that you hear, the news, are always going to be in here. So pick your project. Pick your project. Okay. So for example, let me give you an example of these things because it goes back a little further. Things like precision farming. Again, precision farming is nothing new now. It's still considered emerging technology because it hasn't. We'll go to when it stopped becoming emerging technology and just regular technology. Okay. But to my mind, precision farming is still not just technology. It's still emerging technology. Okay, and then we'll go to definition of emerging. So these are basically, at some point, if you're gonna pick your project, you're gonna say, I'm over here, I'm over here, I'm over here, I'm in here. I don't think any one of you are going to atomic bomb kind of project. Never know. Okay, so precedents. Okay, so again, everything traced back to scientific discovery. You know the difference between invention and innovation. I think I'll say just one sentence, right? Innovation is not invention. Invention is not innovation, right? Invention is to make something possible. Innovation is when it becomes viable. That viability has many adjectives to it. Economic viability, marketing viability, environmental viability, social viability, political viability, all kinds of stuff, logistic viability. Okay, unless those things comes together, innovation don't really take off. Once the innovation take off, becomes common ground, it's just about application. Okay, nobody thinks of Excel spreadsheet as an innovation, right? Do you? Okay, in my year it was. When I was your age, we had Lotus 1, 2, 3 as a spreadsheet, go, one block at a time. So Excel with this menu driven, wow, that's a cool thing, that sort of thing, right? You guys don't think of Excel as innovation. I don't either, right? Now it's just application. Use Excel to do accounting, you do Excel to this and that, whatever, okay? And again, application is societal dimension, military government, commercial economics. This is where Basai students are focused. I'm running out of voice soon. Anyway, so now, what makes something emerging? Okay, and this is why you can't do a lifelong learning on Excel spreadsheet, right? Because it's not emerging technology anymore, right? What makes it has to involve a fraction of humanity. Okay, it's not everywhere yet. Okay, that's just sort of like an easy way of saying that things begin small. Okay. So the key idea is that, and this is something I want to spend a sentence on it. The fraction of humanities are not homogeneous. In other words, there's a different role that fraction, small as it is, play. Some play promotion. Oh, I'm really big on Bitcoin. Okay. Some play on the technology. Some play on the social dimension. Some play. So they're driving emergence in various capacities. Okay. I'm doing my capacity as a teacher. Okay. Somebody's doing it capacity as a commercialization. Okay. So not only does it involve just a small fraction, but there are many jobs in that fraction. Okay. Whereas if you're talking about things like Excel is a good example. Excel is no longer emerging technology. What do most people do? Well, are they developing? Are they selling? Are they promoting? No, most of them are just using. That's it. They're not doing different jobs. They're just using. Okay, so once emerging become common day knowledge, it just used it. Okay, but while it's still emerging, there are different. What I mean here is that this is where Basai student reads their future. What am I going to do vis-a-vis this technology? Am I going to be trying to make money off it? Am I trying to be the guy trying to run a training session? Am I going to be the one who hooks up manufacturing with the theoretical research? There are many roles in it. Okay, whereas that there aren't that many roles left with Microsoft Excel, right? With emerging technology, so many roles in it. Some more techy than the other, some more nerdy than the other, some more math, some less math, some more radioactivity risk, some less, all kind of stuff. And then the second thing that marks emerging, yeah, let me know, by the way, if it's hard time. Sometimes I tend to forget. Okay, I'll just finish this thing and then we'll take a break. Second thing is, in terms of feasibility, it's at a stage. Okay, it's not that static. Okay, Microsoft Excel, just different version every year with a little bit more feature. That's it. There's no such thing as a stage. It's not at a stage anymore. Okay, if at anything, it's sort of like at the stage of dying down, being replaced. But with emerging technology, you can always describe it in terms of stage. We are moving fast toward, feasibility, validity testing, reliability, right? ChatGPT came out, feasibility done, feasibility check, reliability not yet, right? So there's this kind of stage. There's this thing. There's this validity, reliability. They talk about ChatGPT, human alignment, that sort of thing, right? We're talking about it now, right? Maybe in 5 years' time, we won't talk about validity or reliability or alignment. We'll talk about something else, maybe the threat or something, I don't know. Okay, so there's something that characteristically marks what emergent is, that it is a stage thing. It's not hard and fast, but it is a stage. And yet, there is no. Let me click that. So the name of the game is gaining traction. Okay, and it turns out that the more stages you progress, the more traction you get. But you also have to get traction at each stage. Let me say that again. So traction has two meanings. Okay, so at the feasibility stage, let's say feasibility, it has to gain traction. In which case that means people accept it's a feasibility. So we go to reliability, it has to gain traction, meaning enough people believe it's reliable. Okay, ChatGPT gained traction right away in terms of usage, because 1 month after its release, you got 100 million active user. Now they may not know what they're doing, but they're doing it, right? So it's gaining traction at each stage. And then as you have more stages, the whole thing is about gaining traction vis-a-vis the whole society. Okay, so at some point, once ChatGPT moves beyond, nice thing to chat around with your friends or meme thing, to the validation, to ability for it to generate scientific hypotheses being tested and so forth, then it starts to gain traction in scientific community, in academic, becomes normal thing. It becomes something that you reliably discuss as part of being a human society. Okay. In the meantime, well, let's go back to Excel. Okay. When Excel was invented, let's say, okay, does it necessarily, is it important? Is it set in stone that when you go down the row, you go in numbers, and you go across, you go in A, B, C, D? It's not, right? Could it be the other way around, right? Excel could have been designed so that you access the column by Greek alphabet, right? And the row by Roman numerals. I don't know. Okay, that's a bit silly. Okay, the point is that all these specificities, this norm, this what makes a standard look and feel? What makes it take for granted that this is what you're going to see? This kind of modality of how you work with it by clicking down. None of this is set. There's no standard. There's not convention. There's no convention yet because people are trying different things. When the mouse was invented, they could have invented so that right-handed people use mouse on the left-hand side. Okay, right? With 5 buttons. Okay, now it's pretty much set in stone. If you're right-handed, you use mouse on the right-handed, right? And there are 2, maybe 3 versions, either 2 buttons or 1 button with a little bit of scroll. Okay, so, and things don't deviate much from it. It's just a little tweaks now. Okay, again, modality not yet. Think of airplanes, right? Airplanes, you have big wing in the back, small wing in front, but now virtually wherever you go, you get big wing in front, small wing in the back, right? If it's commercial jet engine hangs in the middle. Okay, so they're like even out the axis. But if you're talking about emerging technology, there's no acceptance. There's no saying, okay, you go across the row, we use number. Across column, we use A, B, C, D. Okay, which is a bit silly, right? Once you go to A, B, C, D, go A, you know. But back then, it's already set in stone because at that time you didn't have that many columns. Okay, so maybe in hindsight, it would have been better if you used number for both row and columns, which is what mathematicians do, right? And also, you notice, because you start with alphabet on the column, when you access cell, you go column first, right? Right? So G27, you go to G column, 27 row. Whereas when you work with matrix, you go to row and then column, okay? So that doesn't make too much sense, but so what? It's stuck already, okay? So one of the things that marks out something that's no longer emerging technologies is that, you know, any kind of design imperfection is already set in stone. It's a bit like language, by the way. Language is a bit like that. Language has funny quirks. Every language has a quirk. English, German, Japanese. But so what? People have stuck with it. It stays. Okay? So it's no longer emergent. It's just evolving. Okay? It's not emerging. So keep in mind, these are sort of like hallmark of what makes something emergent. Okay? So it's small. It's not everyone. And different people have different role to play because there's so many things to do with it. Marketing, proof of concept, all kind of stuff. It's at a stage, right? We talk about stage and gaining traction, okay? And the way things are done are not quite set in stone. People are sort of like, yeah, should we do this and that sort of thing, okay? But once you get beyond this, everything looks the same, okay? So Chinese company come up with a Excel, a spreadsheet, WPS, same thing, guarantee you. Go to column, it's ABC, row, 1, 2, 3. Right? They're not going to do anything else because nobody's going to like it. Now, historicity, it just means this is not a main point because this is where you're moving. The only thing you need to realize is that you are in a post-digital society. Okay? Anything that came before you has already been digitized. Good example, when I was your age, a lot of things were digital. But certainly telephone weren't. Right? My car wasn't digital. In other words, when I accelerate, my pedal is a mechanical wire. Now, if you press accelerator, it activates a signal to the ECU to apply more gas. Well, not all cars do that, but you see what I mean? Yeah, it's digitized. It's called throttle by wire. Okay, so maybe not all cars do that. That's fine. I'm not saying all cars have to be that, but everything that could possibly be done has been digitized. Okay, I'm just saying that right now. Okay, now it's going to be more, but just say virtually everything. There's nothing you can tell me that has not been digitized. in some form. Yeah. And a car throttle is a good example. Let's take a break.